The moment we try to take the next step in understanding reality, we run into a wall that has been standing quietly in our path for decades. We can describe the universe using the language of quantum mechanics, and we can describe the universe using the language of Einstein's gravity, but the two dialects refuse to speak to one another. Somewhere between the smallest flicker of energy and the deepest bend of spacetime, a missing word waits to be discovered. Most physicists believe that missing word is a particle, the quantum unit of gravity, the graviton, yet it seems the universe itself may have arranged the rules so that we never, ever see it. It is as if the cosmos has been designed to reveal everything except its final layer. We can hear black holes collide from billions of light years away. We can map the faint afterglow of the Big Bang. But when it comes to the particle that should stitch the fabric of space together, the universe lowers the lights and locks the door. The question is simple to ask and painfully hard to answer. Is it actually possible to catch a graviton? Or are we trying to pry open a secret that the laws of physics were written to protect? The graviton is meant to be the quantum messenger of gravity, the same way photons carry electromagnetic force and gluons carry the strong nuclear force. But it is more than a messenger. If gravity is truly quantum, then every stretch, ripple, and vibration of spacetime is ultimately built from an ocean of these particles. The calm emptiness between galaxies, the crushing interior of a neutron star, the silent vacuum you picture when you imagine outer space, all of it would be made from countless gravitons flickering in and out of existence. We have learned how to detect gravity in its classical form with extraordinary sensitivity. Interferometers with arms several kilometers long can register distortions smaller than a proton. These machines have already transformed astrophysics, letting us listen to distant cosmic catastrophes. But those detections involve gravitational waves, vast coherent swarms of gravitons acting together like a tide. The challenge before us is to strip that tide down to a single drop. To appreciate the scale of the problem, imagine the most sensitive gravitational wave detector you can build. Laser beams race back and forth between mirrors suspended in vacuum, their phases compared with exquisite precision. A passing gravitational wave slightly changes the distance between the mirrors, shifting the pattern of light. That shift is so small that it is better thought of as a change in length measured in fractions of atomic nuclei. And yet, even this heroic level of sensitivity corresponds not to one graviton, but to a stupendous number of them acting in unison. The smallest wave we can currently detect contains more gravitons than there are grains of sand on Earth multiplied by the number of stars in the Milky Way. To isolate a single graviton through this method, we would need to improve our sensitivity by an absurd factor. The variation in length we would need to measure is on the order of the Planck length, the distance scale where the concept of space itself becomes fuzzy. At that point, familiar ideas such as location and motion stop behaving in the way everyday intuition expects. The difficulty is not merely technological. It is rooted in the way nature balances knowledge and disturbance. To measure the separation of two mirrors with extreme precision, we must bounce light between them. But light carries momentum, and when it strikes a mirror, it nudges it, however slightly. The more accurately we try to locate the mirror, the harder we must hit it with photons, and the more we disturb its motion. This trade-off is not a flaw of our instruments. It is a built-in feature of the universe. We can try to beat this limitation by changing the experiment. Make the mirrors heavier so they move less when struck. Bring them closer together so the measurement happens more quickly. But if we push both of these ideas to their logical extreme in pursuit of Planck-scale precision, something bizarre happens. The mass and density required to stabilize the mirrors cause them to collapse under their own gravity. They form a black hole, complete with an event horizon that seals off the very region we are trying to measure. Our detector becomes a cosmic trapdoor that swallows the information we seek. In this way, the universe seems to pull a trick worthy of a magician. The moment we attempt to observe the fundamental unit of gravity directly through its effect on space-time, space-time itself folds over the apparatus and erases the experiment. It is not that we lack cleverness. It is that the stage vanishes beneath our feet. So perhaps we should stop trying to measure gravity as a wave and instead treat the graviton like any other quantum particle. When physicists first suspected that light came in discrete packets, they did not look for ripples in an electromagnetic field. They studied collisions, absorptions, emissions. They let photons knock electrons out of metal plates and leave unmistakable fingerprints in detectors. Why not apply the same strategy to gravity? The most dramatic expression of this approach is the particle collider. To reveal new particles, we hurl known particles at one another at extraordinary energies and sift through the wreckage. The catch is that gravity is unimaginably weak compared with the other forces. On the scale of everyday life, this weakness is hidden by the enormous mass of planets and stars, but in the microscopic realm, it becomes crippling. The chance that two particles will emit or absorb a graviton during a collision is so small that it might as well be zero for any machine we can realistically build. To raise that probability, we must raise the energy of the collisions. At sufficiently high energies, gravity begins to compete with the other forces. But sufficiently high here does not mean a few times more powerful than our current accelerators. It means energies that dwarf anything humanity has ever produced. If we took today's most powerful particle collider and tried to scale it up to the point where graviton production became likely, the resulting machine would not fit on Earth. It would not fit within the solar system. It would sprawl across interstellar space. Even if we somehow constructed such a monstrosity, creating gravitons would only be half the battle. Detecting them would remain an almost comical challenge. Gravitons are massless and stable. They do not decay into more convenient particles. They barely interact with anything at all. Their interaction cross-section, the effective size they present as a target, is so tiny that a graviton could pass through a solid planet without noticing it was there. You might imagine adapting the photoelectric effect for gravity. In that classic experiment, a single photon can knock an electron free from a metal surface. In principle, a graviton of high enough energy could do the same, but the odds of such an event are so small that you could cover the Earth in detectors and wait longer than the age of the universe for a single, clear signal. Nature does provide its own graviton factories. The dense, scorching cores of stars churn out an ocean of gravitational quanta. Collapsed stellar remnants such as white dwarfs and neutron stars are even more prolific. Streams of these particles pass through your body every second, and yet they are so shy that over the entire history of our planet, only a handful would be expected to have interacted with anything inside it. There is another trick, one that at first glance seems to offer a loophole. Under certain conditions, gravitational waves and electromagnetic waves can transform into one another. Place a powerful magnetic field along a long, empty cavity. Aim it at a source of gravitational radiation, and some of those gravitational ripples might convert into ordinary light. Detect the light, and you have indirectly detected the graviton. But here again, the universe intervenes. The magnetic fields required are so intense that the vacuum itself begins to misbehave, spawning particle-antiparticle pairs that disrupt the delicate resonance needed for the conversion. The very emptiness of space rebels against the attempt. One by one, the strategies fall apart. When we try to measure space-time at its smallest scale, it collapses into a black hole. When we try to manufacture gravitons and collisions, we need machines the size of star systems. When we try to catch naturally occurring gravitons, they slip through all matter as though it were fog. And when we attempt to coax them into revealing themselves through clever quantum tricks, the vacuum tears the apparatus apart. It is difficult not to feel that we are being deliberately frustrated, not by some conscious agency, but by the deep structure of the laws themselves. The graviton may exist, and in overwhelming numbers, yet be permanently hidden from direct view. We may be left to infer its presence only through indirect clues, forever circling a truth we can never quite touch. Still, history has taught us caution in declaring any scientific goal unattainable. The same was once said of atoms, of the interior of stars, of the curvature of space-time. Each time, a new idea or a new technology reshaped the landscape. Perhaps the universe is not hiding the graviton from us, but daring us to think in ways we have not yet imagined. The unsettling possibility is that gravity may not simply be difficult to quantize, but fundamentally resistant to being cornered into the same experimental traps we use for other forces. When we reflect on the history of physics, every great advance has followed a familiar pattern. We see something strange in nature, build an instrument to isolate it, and then refine that instrument until the effect becomes routine. But gravity does not behave like a reluctant guest who can be coaxed into the room. It behaves like a shadow that vanishes whenever we try to shine a direct light on it. To understand why, it helps to step back from laboratories and machines and look at what gravity really is. It is not just another force acting in space. It is the geometry of space itself. When mass and energy are present, space-time bends, and objects follow the curves that result. If space-time is made from gravitons, then trying to detect one is not like trying to catch a photon or a neutrino. It is more like trying to isolate a single ripple in the shape of reality while standing inside that shape. This difference becomes stark when we compare gravity to electromagnetism. Photons can be blocked, reflected, focused, or absorbed. We build mirrors for light, lenses to bend it, antennas to gather it. There is no mirror for gravity. There is no lens that can focus a graviton beam the way glass focuses sunlight. Gravity ignores every material boundary we can conceive. A graviton emitted at the heart of a star passes effortlessly through layers of plasma, rock, water, metal, and flesh without changing course. That transparency is not an accident. It is a direct consequence of gravity's weakness at the quantum level. The coupling between a graviton and an electron is so feeble that the electron may as well not exist from the graviton's perspective. Multiply that electron into a mountain or a planet, and the story does not change much. You get more chances for interaction, but each chance is so small that the total still barely registers. Consider the neutrino, a particle long regarded as the epitome of elusiveness. For decades, physicists were unsure whether it even had mass. We now build detectors filled with vast volumes of water or ice, waiting patiently for a rare flash of light that signals a neutrino interaction. Even so, most neutrinos from the Sun pass straight through Earth, as if it were empty space. Yet compared to gravitons, neutrinos are positively sociable. For every graviton that might interact with a detector, an almost incomprehensible swarm of neutrinos will produce noise. This raises a sobering question. Suppose, by some technological miracle, we succeeded in constructing a detector large enough, sensitive enough, and isolated enough to register the gravitational absorption of a single graviton. How would we know it was a graviton and not something else? The signal would be lost in a storm of other interactions, each masquerading as the very effect we are hunting. One might hope that the universe itself could provide us with a natural experiment, some cataclysmic environment where gravity is so intense that its quantum nature becomes unavoidable. Black holes are obvious candidates. Their horizons are regions where space-time is bent to an extreme. If gravitons are real, then black holes must be among the most prolific emitters or absorbers of them. But black holes are also the ultimate hoarders of information. Anything that crosses the event horizon is cut off from the rest of the universe. If gravitons do something interesting there, that story is locked behind a curtain that never lifts. There is also the early universe to consider. In the first instance after the Big Bang, energies were enormous, and gravity was likely as strong as the other forces. That era may have left behind subtle imprints in the distribution of matter and radiation we observe today. Those imprints are indirect whispers of a time when quantum gravity ruled. But whispers are not sightings. They tell us that something happened, not exactly what. The tension here is philosophical as well as technical. Physics has always rested on the assumption that whatever exists in nature can, at least in principle, be observed. The graviton challenges that assumption. It tempts us with a picture of reality that is structurally complete and yet experimentally sealed. A theory may be mathematically consistent, aesthetically compelling, and unifying, and still forever beyond the reach of a detector. This leads some thinkers to entertain the idea that quantum gravity may be fundamentally different from other quantum theories. Perhaps spacetime does not admit particle-like excitations in the way fields do. Perhaps the graviton is not a particle in the conventional sense, but a bookkeeping device, a convenient fiction that emerges in equations without ever manifesting as an isolated event in the world. Yet abandoning the graviton is not so simple. The frameworks that seek to merge quantum mechanics and general relativity almost all require it. Without some quantum carrier of gravitational influence, these theories lose coherence. The graviton is woven into their mathematics as deeply as the photon is woven into quantum electrodynamics. So we find ourselves in a peculiar limbo. Our best ideas demand the graviton. Our best experiments repel it. It is as though the universe has offered us a blueprint for its foundations, but has erased the instructions for verifying them. Still, the story may not end in defeat. In recent years, a new line of thought has emerged that reframes the problem. Instead of trying to detect gravitons directly, perhaps we can detect the quantum nature of gravity by watching how it entangles other systems. Quantum objects placed in gravitational fields might become subtly linked in ways that cannot be explained by classical physics. Such effects would not show us a graviton, but they would reveal that gravity itself participates in the quantum game. These ideas are still tentative, and their experimental realization would be extraordinarily delicate, but they hint at a strategy that sidesteps the universe's apparent traps. If spacetime will not let us pluck out a single graviton, perhaps it will allow us to feel its quantum texture through the way it binds other things together. This shift in perspective does not make the challenge easier, but it does make it different. Instead of trying to corner gravity as if it were a shy animal, we begin to treat it as the stage on which all quantum dramas unfold. We listen not for the footstep of the graviton, but for the subtle change in rhythm that its presence might impose on the dance of matter. If this approach succeeds, it will mark a profound change in how we think about observation itself. For centuries, measurement has meant interaction. We see because light bounces off things and enters our eyes. We know about electrons because they leave tracks in chambers or sparks in silicon. The graviton seems to mock this tradition. It refuses to leave footprints. Instead, it invites us to infer its existence from the choreography it enforces on everything else. To grasp what this might look like, imagine placing two tiny objects into a state where quantum theory says their properties are linked. This phenomenon, entanglement, means that measuring one immediately influences the other, regardless of the distance between them. Now, imagine that these objects are linked not by an electromagnetic field or by a physical wire, but by nothing more than their mutual gravitational attraction. If such an experiment were realized, and the entanglement could be shown to arise solely from gravity, it would imply that gravity must itself be quantum. Classical fields cannot generate quantum entanglement. Only a quantum mediator can do that. This is a subtle argument, and it does not give us a graviton to hold in our hands, but it would be the closest thing yet to seeing gravity's quantum face. It would be like discovering the existence of air not by catching a molecule in a net, but by watching leaves sway in a breeze no one can see. The challenge, of course, is that gravity between small objects is incredibly weak. The gravitational pull between 2-millimeter-sized spheres is so tiny that it is overwhelmed by stray electric charges, thermal vibrations, even the gentle push of light itself. To observe gravitationally induced entanglement, we would need to isolate these objects from every conceivable disturbance and keep them in exquisitely controlled quantum states. The experiment would be a masterpiece of patience, precision, and persistence. But even this route does not entirely escape the graviton's elusiveness. At best, it would demonstrate that gravity behaves like a quantum field. It would not reveal the individual quanta. The graviton would remain an inferred entity, like the unseen gears inside a clock, whose ticking we can hear but whose mechanism we never open. There is a deeper question lurking beneath all of this. Why is gravity so different? Why is it that the force that shapes galaxies is the same force that refuses to show its face in the quantum realm? Some physicists suspect that this is not an accident, but a clue. Perhaps gravity is not a force in the same category as the others. Perhaps it emerges from something more fundamental, the way temperature emerges from the motion of atoms. In that picture, the graviton might be like a phonon in a crystal, a collective vibration rather than a true elementary particle. If that is the case, then our insistence on detecting a graviton may be misplaced. We do not hunt individual sound quanta in the air when we study acoustics. We work with waves, with pressures, with patterns that arise from deeper layers of reality. Gravity might belong to that class of phenomena, describable in quantum language, but not reducible to a neat particle that can be plucked from the void. Yet even this interpretation does not entirely resolve the paradox. If gravity is emergent, it still must mesh with quantum mechanics in some coherent way. The universe does not care about the categories we invent. It obeys a single set of rules, whether we understand them or not. And so the graviton continues to haunt the equations, a spectral presence that refuses to become corporeal. One cannot help but reflect on the emotional undertone of this quest. There is a human desire not just to explain the universe, but to touch it, to feel that the abstractions in our theories correspond to tangible things. The graviton denies us that satisfaction. It suggests that the deepest layer of reality might be knowable only through patterns and consequences, never through direct encounter. There is also a cautionary tale here about hubris. Time and again, physicists have proclaimed the end of mystery, only to discover new layers of complexity. Perhaps the graviton is teaching us humility. reminding us that some questions may be answerable only obliquely, or not at all. And yet the story is not finished. The same ingenuity that once turned invisible radiation into everyday medical tools, that transformed the flicker of atomic spectra into lasers and transistors, is still at work. New materials, new methods of quantum control, new ways of isolating systems from noise are being developed. Each advance chips away at what once seemed immovable. There is a poetic symmetry in this struggle. Gravity governs the largest structures in the cosmos, sculpting clusters of galaxies and guiding the motion of stars. Quantum mechanics governs the smallest, orchestrating the behavior of particles in a whisper of space. The graviton is the bridge between these extremes. Its apparent invisibility is not a failure of imagination, but a reflection of the sheer audacity of the task. We are trying to unite the whisper and the thunder, the tremble of an atom with the roar of a supernova. Whether we ever succeed in isolating a graviton, or whether we are forever confined to indirect hints, the pursuit itself reshapes our understanding. It forces us to question what it means to observe, what it means for something to exist, and how the universe parcels out its secrets. In chasing a particle that may never be caught, we may discover something even more profound about the nature of reality. The pursuit of the graviton also exposes a fault line in how we define success in science. Is a theory validated only when its predicted particles are directly observed? Or can coherence and explanatory power suffice? For much of the 20th century, the prevailing answer favored observation. The neutrino, the positron, the Higgs boson all traveled the same path from mathematical necessity to experimental confirmation. Each was once considered fantastical, and each eventually emerged from the noise of detectors to take its place in textbooks. The graviton threatens to break that pattern. It may remain a resident of equations rather than laboratories, an entity that helps our theories hang together while forever eluding the apparatus we build to test them. If that happens, the philosophy of physics will have to stretch to accommodate a new category of knowledge, one in which certain aspects of nature are accessible only through their influence on other things. This tension is already visible in the way we talk about spacetime. We do not observe spacetime directly. We observe clocks ticking at different rates, light bending around massive objects, and orbits precessing. From these behaviors, we infer curvature. The graviton, if it exists, would simply be the quantum refinement of that inference. Instead of observing a particle, we would observe the way its absence or presence reshapes the world around it. There is also the practical question of scale. Much of modern technology depends on exploiting the discrete nature of energy and matter. Semiconductors, lasers, magnetic resonance imaging all rest on the fact that particles exchange energy in quantized packets. Gravity, by contrast, is so smooth and so pervasive that it appears continuous. Even when we listen to the violent merger of black holes, we hear a swell and fade that resembles a classical wave more than a rain of particles. Perhaps our instruments are simply too crude to hear the individual notes in that cosmic symphony. Or perhaps the symphony has no notes, only a melody that emerges when countless unresolvable elements act together. If the latter is true, then the graviton may be more like the concept of a wave crest in the ocean, a useful abstraction that cannot be bottled. Still, it is difficult to abandon the hunt. The idea that spacetime has a granular structure at the smallest scale is too compelling, too central to the dream of unification, to let go lightly. Without it, we are left with two incompatible descriptions of reality stitched together by hope rather than proof. The universe may also be offering us a different kind of challenge. Instead of asking us to detect the graviton, it may be daring us to rethink what detection means. The methods we inherited from classical physics are based on the notion of disturbance. We push on things and see how they move. But quantum systems do not yield their secrets so simply. They can be coaxed into revealing correlations, probabilities, patterns that are invisible to any single measurement. Gravity may be inviting us into that more delicate mode of inquiry. Imagine a future experiment in which two microscopic objects, isolated from everything but each other, slowly drift into a shared quantum state under the influence of gravity alone. There would be no flash, no particle track, no sudden event to mark the moment. Instead, there would be a gradual weaving together of possibilities, a statistical signature that only quantum gravity could explain. It would not feel like discovery in the old sense. It would feel like eavesdropping on a conversation the universe thought no one was listening to. And even then, skeptics would ask whether we had really seen a graviton or merely a shadow cast by something deeper. The debate would continue, as it always does, refining our questions as much as our answers. There is a quiet irony in all this. The same force that keeps our feet on the ground, that holds our planet in orbit around the sun, that anchors our galaxy in the cosmic web, is the one that refuses to show its smallest face. We are surrounded by gravity every moment of our lives. Yet the more closely we look, the less tangible it becomes. Perhaps that is the lesson. The universe is under no obligation to reveal itself in the forms we find most convenient. It does not care that we like particles we can point to, graphs we can draw, detections we can celebrate. It offers us patterns, and it is up to us to decide how to read them. Whether the graviton is ultimately caught, inferred, or quietly set aside, the journey toward it reshapes our understanding of what it means to know anything at all. We may discover that some truths are not objects to be captured, but relationships to be understood, threads woven through the fabric of experience that can never be fully disentangled. There is a temptation, when faced with a challenge that seems so intractable, to imagine that the problem lies in our tools rather than in the universe. We picture ever more refined detectors, ever colder laboratories, ever larger machines, and assume that persistence will eventually win. But the graviton problem suggests that persistence alone may not be enough. It hints that the architecture of reality itself imposes a boundary on what can be pulled into the light. To see why this boundary feels so alien, consider how naturally other particles fit into the logic of experimentation. An electron has charge, so it bends in a magnetic field. A photon has energy, so it heats matter and liberates electrons. Even neutrinos, those ghosts of the particle world, occasionally leave telltale flashes when they strike the right target. Each particle carries with it some handle that allows us to grip it. The graviton carries only gravity, and gravity is geometry. A graviton does not push or pull in the ordinary sense. It subtly reshapes the stage on which all pushes and pulls occur. Trying to trap it is like trying to grab a wrinkle in a tablecloth while standing on the table itself. The wrinkle is real, but it does not present itself as an object independent of the surface. This may explain why so many proposed detection methods collapse into paradox. To see a graviton through its gravitational effect, we must measure distances with absurd precision, and that act creates black holes. To see it through collisions, we must reach energies that make spacetime itself unstable. To coax it into revealing itself through conversion into light, we must generate fields that tear the vacuum apart. Each attempt is thwarted not by engineering, but by the very laws that make the attempt meaningful. At some point, we must ask whether the graviton is an entity in the same sense as the particles we already know. When we say that a photon exists, we mean that there are situations in which it can be counted, absorbed, reflected, or emitted in isolation. There is no comparable situation for a graviton that does not immediately dissolve into conceptual difficulty. One radical response is to take this seriously and to reimagine quantum gravity not as a theory of particles, but as a theory of information. In this view, space-time is not made of things, but of relationships. The fundamental units are not gravitons, but bits of correlation, patterns of entanglement, that give rise to geometry as a byproduct. Gravity then becomes the large-scale expression of how information is arranged and shared across the universe. This idea, once considered fringe, has steadily gained traction because it dissolves some of the graviton's paradoxes. If spacetime emerges from entanglement, then it is not surprising that its putative particle is elusive. You cannot isolate a relationship in the same way you isolate an object. You can only infer it from the network in which it is embedded. Yet even this perspective leaves us uneasy. It trades one mystery for another. Instead of asking where the graviton is, we ask what information is and why it should organize itself into something that feels like space. The questions shift, but they do not vanish. There is also the human dimension to consider. Much of the drive to detect the graviton comes from a desire for closure. The 20th century delivered two towering frameworks, quantum mechanics and general relativity, each astonishingly successful in its own domain, but together they form an unfinished story. The graviton is the missing character whose appearance would tie the narrative together. Without it, we are left with a book that has two brilliant halves and no satisfying ending. Perhaps the universe is indifferent to our narrative instincts. Perhaps it does not care whether its story feels complete to us. Still, the search continues, not just out of stubbornness, but out of curiosity. There is something deeply compelling about a problem that resists every assault. It acts like a mirror, reflecting our assumptions back at us. Each failed attempt to detect the graviton teaches us something, not about the particle, but about the limits of our methods. We learn, for example, that there is a minimum scale to meaningful measurement, that space-time cannot be probed arbitrarily finely without ceasing to behave like space. We learn that weakness at the quantum level can translate into invisibility at the macroscopic level. We learn that the vacuum is not empty, but structured in ways that can sabotage our best-laid plans. These lessons accumulate into a broader wisdom. They suggest that the universe is not a passive object waiting to be examined, but an active participant in the act of examination. It responds to our questions, sometimes by answering them, sometimes by changing the rules of the game. In that light, the graviton is not merely a missing particle. It is a boundary marker, a signpost pointing to the edge of our conceptual map. Whether we eventually cross that boundary or learn to live with it, the journey toward it reshapes our understanding of what physics is and what it can hope to achieve. To keep moving forward in this story, it helps to remember that science has faced walls before. At the end of the 19th century, many physicists believed that the laws of nature were essentially complete. Only small refinements, they thought, remained. Then a series of stubborn anomalies forced the birth of relativity and quantum mechanics. Each time, the universe had been whispering that our categories were too narrow. The graviton may be whispering something similar now. It may be telling us that our classical notion of a particle is inadequate for the task at hand. When we talk about particles, we imagine little marbles flying through space, occasionally colliding. But quantum theory long ago taught us that this picture is an approximation, a convenience. Particles are excitations of fields, and fields are not things in the ordinary sense. They are more like possibilities that become real only when they interact. Gravity complicates this further because its field is not laid out on space-time. It is space-time. The gravitational field is the geometry within which all other fields reside. So to speak of a graviton as a ripple in that field is to speak of a ripple in the fabric of the arena itself. It is a concept that strains the metaphors we inherited from earlier physics. This conceptual strain shows up whenever we try to imagine what a single graviton looks like. Does it have a wavelength? A polarization? In the equations, yes, but those properties are defined with respect to a background spacetime. If spacetime is itself fluctuating, the background is part of the phenomenon. The graviton is not a thing in space. It is a tiny, transient reshaping of space. One consequence of this is that gravitons may not be localizable in the same way as other particles. We localize a photon by absorbing it in an atom. The atom changes state, and we say the photon was here. To localize a graviton, we would need an object that can absorb a tiny chunk of geometry. But any object capable of doing that would have to interact gravitationally in a way that our current understanding simply does not allow. This blurring of locality has another implication. It suggests that the graviton might not be detectable as an isolated event because it is not an isolated event. It is a collective adjustment of relationships across a region of spacetime. Trying to see it is like trying to point to a single crest in a stormy ocean and declare that crest to be a thing apart from the water around it. Yet the language of particles persists because it is so useful. It lets us calculate, predict, and communicate. The graviton, as a mathematical entity, is indispensable in many approaches to quantum gravity. It allows us to write down interactions, to explore how gravity might behave at very high energies, to test the internal consistency of our ideas. In that sense, it is as real as any other theoretical construct. The question is whether that reality ever crosses into the laboratory. Some physicists suspect that the answer may depend on the scale at which we choose to ask the question. At everyday energies, gravity is feeble and smooth. At the Planck scale, it may be wild and granular. The graviton, if it exists as a particle, might be a creature of that scale alone. If so, then detecting it would require not just better machines, but access to a regime of nature that is effectively sealed off from us. This idea reframes the problem in a sobering way. It is not that we have not yet found the right experiment. It is that the right experiment may be impossible to perform in our universe. with our laws and our limits. The Planck scale may be a kind of horizon, not in space, but in knowledge. And yet, horizons are meant to be crossed. The event horizon of a black hole is a barrier to light, but not to imagination. We study what happens there through theory and through the subtle effects black holes have on their surroundings. In the same way, the graviton horizon may be breached indirectly through patterns that only quantum gravity can produce. One such pattern could lie in the very structure of spacetime noise. If spacetime is made of discrete elements, it may never be perfectly smooth. There may be a faint jitter, a restless shimmer that pervades even the emptiest regions of the cosmos. This noise would be unimaginably small, but it might accumulate over vast distances or long times in a way that leaves a measurable trace. Detecting such a trace would be like hearing the hum of individual atoms in a cathedral. The sound is not any one atom, but the collective whisper of countless unseen motions. In this scenario, the graviton is not heard as a single note, but as part of a background murmur that only the most sensitive instruments can discern. Whether this murmur exists is an open question, but the very act of asking it stretches our understanding of what the universe may be hiding. The graviton becomes less a quarry to be captured, and more a lens through which to examine the boundaries of human inquiry. The boundaries of inquiry are rarely comfortable places to linger. They force us to confront the possibility that some aspects of the world may remain forever beyond our direct grasp. Yet those boundaries are also where the deepest insights often emerge. When we stand at the edge of what we can test, we are compelled to refine not just our tools, but our language, our concepts, and even our expectations. The graviton sits precisely at such an edge. It is the natural bridge between two pillars of modern physics, and yet it is also the point where those pillars seem least willing to touch. We know how to quantize fields that live in spacetime. We know how to describe spacetime as a smooth, geometric object. What we do not know is how to quantize the stage itself without tearing it apart. In the classical world, a stage is passive. It does not care what actors perform upon it. In the quantum world, the stage and the actors are entangled in a way that defies our everyday intuition. If spacetime is a quantum entity, then it is both stage and actor at once. The graviton is the symbol of that duality. This duality also infects the way we think about measurement. In ordinary quantum experiments, we assume a fixed background in which particles evolve and are observed. With gravity, the background is part of the system. Measuring a graviton is not like measuring a photon in a box. It is like measuring the box while you are inside it, using tools that are themselves made from the box. This circularity may be the true obstacle, more than any technological limit. It is not just that gravitons are weakly interacting. It is that the act of defining what it means to observe them presupposes a framework that they themselves are supposed to create. One way out of this loop is to abandon the idea that space-time is fundamental. If space and time emerge from something deeper, then the graviton may not be a fundamental particle at all, but a convenient way of describing certain collective excitations in that deeper layer. This is the same move that condensed matter physics makes when it describes sound in terms of phonons. No one expects to catch a phonon in isolation outside the material that supports it. It is real, but its reality is tied to a larger structure. If gravity is similar, then the graviton may only make sense within a certain regime, a certain approximation. It may be as inappropriate to demand its direct detection as it would be to demand a photograph of a temperature. Temperature is real, but it is not a thing you can point to. It is a summary of how many unseen particles are moving. This analogy is not perfect, but it is suggestive. It implies that the graviton problem is not a failure of ingenuity, but a category error. We may be asking the wrong question of the universe. At the same time, the success of particle physics makes it hard to let go of the particle picture. We have built a civilization on the ability to harness quantized excitations of fields. We send photons through fiber optic cables, manipulate electrons in microchips, and trap atoms in lattices of light. These triumphs bias us toward expecting the same from gravity, yet gravity has always been the odd one out. It dominates on large scales but fades into irrelevance on small ones. It shapes the cosmos but scarcely nudges an atom. It is universal but elusive. The graviton simply concentrates all of these peculiarities into a single, stubborn symbol. There is also the matter of aesthetics. Physicists are drawn to symmetry, to unity, to theories in which the pieces fit together with minimal strain, a universe in which gravity cannot be quantized in the same way as other forces feels lopsided. The graviton promises to restore balance, to place gravity back into the fold. But perhaps the universe does not share our aesthetic preferences. Perhaps it is content with a patchwork of principles that only partially overlap. In that case, the graviton may be a beautiful mirage, a structure that exists only in the mathematical desert where our theories wander. And yet, even mirages can guide travelers. The graviton has already led to profound developments in theoretical physics. It has forced us to confront the limits of locality, the meaning of measurement, the possibility that spacetime is emergent, and the role of information in the structure of reality. These are not small achievements. Whether or not a graviton is ever detected, its pursuit has altered the landscape of thought. It has shown us that the deepest questions are often those that resist the most direct answers. It has taught us that to understand the universe, we may need to become comfortable with inference rather than inspection, with patterns rather than particles. As the search continues, another layer of complexity comes into view, one that has less to do with particles and more to do with time. Gravity does not merely curve space, it stretches and compresses time as well. Clocks tick differently in gravitational fields, a fact confirmed countless times in practical technologies that rely on precise timing. If gravity is quantum, then time itself must participate in quantum behavior at the deepest level. That is a disquieting thought. In ordinary quantum mechanics, time is treated as a background parameter, a universal metronome against which change is measured. But in general relativity, time is part of the dynamical fabric. It slows near massive objects and speeds in emptier regions. The graviton, if it exists, would blur the distinction between what is measured and what measures. A quantum of gravity would not just jiggle distances, it would subtly shuffle the ordering of events. This raises questions that border on the philosophical. What does it mean to speak of a quantum of time? Can there be uncertainty in when something happens, not just in where or how fast? And if so, how could such uncertainty ever be detected when all of our clocks are themselves built from the very space-time that would be fluctuating? The problem circles back on itself. We cannot use time to measure the quantum nature of time without presupposing that time is well-defined. The graviton problem is not isolated. It is entangled with the deepest puzzles about the nature of temporal order. Some researchers have tried to sidestep this by imagining experiments in which time is treated relationally. Instead of asking when something happens in an absolute sense, they ask how one process compares to another. If two quantum systems influence each other gravitationally, perhaps the way their internal clocks drift apart could reveal something about gravity's quantum character. Again, the graviton would not be seen, but its influence would be felt in the misalignment of rhythms. There is also the issue of energy. In quantum physics, energy is exchanged in discrete packets, but in gravity, energy is notoriously slippery. It cannot be localized in a simple way. There is no universally agreed upon definition of gravitational energy density. This is another sign that gravity resists being broken down into bite-sized quanta. The graviton would carry energy, but where would that energy reside? In a field that is identical with the geometry of space? These conceptual tangles suggest that the graviton is not just hard to detect because it is weak. It is hard to detect because it is entangled with our most basic notions of space, time, and energy. It sits at the intersection of ideas that we have not yet fully reconciled. And yet, the universe continues to provide hints that gravity does have a quantum side. Black holes radiate in ways that only quantum theory can explain. The early universe displays patterns that seem to require quantum fluctuations in space-time itself. These are not direct sightings of gravitons, but they are like fingerprints left at a crime scene. They tell us that something quantum is at work in the gravitational realm. We are left in a curious position. The graviton is both necessary and inaccessible, demanded by theory and denied by experiment. It is like a word that completes a sentence we cannot finish speaking. Perhaps the ultimate resolution will not be a triumphant detection, but a quiet shift in perspective. We may come to accept that certain features of the universe are not objects to be observed, but structures to be inferred. The graviton may be one such feature, a conceptual bridge that we cross in our minds rather than in our laboratories. Until then, the question of whether the universe is hiding the graviton from us remains open. It is a question that blends physics with philosophy, technology with humility. It reminds us that the universe is not obliged to be transparent, and that sometimes the deepest truths are those that recede the closer we seem to get. If we accept, even provisionally, that the graviton may never be caught in the traditional sense, we are forced to confront a profound shift in how scientific knowledge might evolve in the future. The 20th century was an era of direct encounters. We smashed atoms and saw their pieces. We bent light and watched it split. We probed nuclei and traced their resonances. The graviton hints that the next era may be defined less by capture and more by constraint. To constrain a theory is to box it in with observations until only one interpretation remains viable. We already do this in many areas of physics. We do not see dark matter particles, but we map their gravitational influence across galaxies. We do not observe the interior of a black hole, but we deduce its properties from how it affects its surroundings. In this sense, the graviton would join a growing family of entities, known only through the shadows they cast. This trend reflects a broader movement in science toward the study of systems that cannot be isolated. Climate, ecosystems, neural networks, and economies are all examples of phenomena whose behavior emerges from complex webs of interaction. Gravity, as the glue of the cosmos, may simply be the most fundamental example of this type of system. Trying to pluck a graviton from it may be as misguided as trying to isolate a single wave from the ocean and call it the sea. Yet there remains an unease in letting go of the particle picture. It is one thing to accept that we cannot see inside a black hole. It is another to accept that a basic building block of reality may be experimentally untouchable. That feels less like a practical limitation and more like a philosophical affront. This unease is sharpened by the success of reductionism, the idea that understanding the parts leads to understanding the whole. The graviton problem suggests that there may be layers of reality where reductionism fails, where the whole is not just more than the sum of its parts, but something that cannot be decomposed at all. There is a possibility that the graviton, like the concept of ether in the 19th century, will eventually be discarded. Not because it is wrong, but because it is unnecessary. The ether was once thought to be the medium through which light waves traveled. It made sense within the physics of the time. But when relativity arrived, the ether faded from the story, replaced by a new understanding of space and time. The graviton could meet a similar fate, supplanted by a framework in which gravity is quantized without ever invoking a particle of gravity. If that happens, future physicists may look back on our era with a mixture of admiration and bemusement. They may see our graviton as a stepping stone, a scaffold that supported the construction of a deeper theory but was never meant to remain. And yet, even if the graviton is ultimately demoted to a conceptual tool rather than a physical entity, its legacy will endure. It has already reshaped how we think about space-time, information, and the limits of measurement. It has forced us to confront the possibility that the universe's most intimate structures are also its most guarded. There is a quiet beauty in that idea. It suggests that the universe is not a puzzle to be solved once and for all, but a conversation to be sustained across generations. Each attempt to corner the graviton is a line in that conversation, a question posed to reality itself. Sometimes the answer is silence, and in that silence we hear not defeat, but invitation. We are invited to imagine new experiments, new principles, new ways of listening to the cosmos. We are invited to expand the meaning of evidence and to reconsider what it means to know something. In the end, whether the graviton is hiding from us or whether it is simply not the kind of thing that can be found, the search for it has already done its work. It has shown us that the universe is deeper than our instruments, subtler than our categories, and richer than any single story we can tell about it. There is a temptation, when reflecting on these ideas, to frame the graviton problem as a failure, as if the universe were denying us a prize we have earned through centuries of careful study. But perhaps it is better understood as a transformation of what discovery looks like. The discoveries of the future may not arrive with the fanfare of a particle trace or a spectral line. They may arrive as the closing of a logical loop, the sudden realization that only one kind of underlying structure could possibly explain the web of phenomena we observe. In that sense, the graviton might be discovered not in a detector but in a proof that gravity must be quantum because no classical theory can account for the way matter behaves in certain regimes. A proof that space-time must have a discrete underpinning because a continuous one leads to contradictions. These would not be the discoveries of instruments, but of ideas, yet their impact could be just as profound. This possibility unsettles the traditional hierarchy in physics, in which theory proposes and experiment disposes. It suggests a more intertwined relationship, where theory and experiment converge on truths that neither can reach alone. The graviton becomes a test case for this new balance. There is also a cultural shift implicit in this. The great experiments of the past were tangible. They involved apparatus you could walk around, machines that filled buildings, events that could be replayed and celebrated. The graviton, by contrast, resists spectacle. Its story is likely to be written in equations and correlations, in faint statistical deviations that only specialists can interpret. The romance of smashing particles together may give way to the quiet drama of inference. Yet even quiet drama can reshape our sense of place in the universe. Gravity is the force we feel most directly in everyday life. It is the weight of our bodies, the pull that keeps us grounded. To realize that this familiar presence is rooted in quantum processes that we may never observe directly is to glimpse a hidden layer beneath the surface of experience. This realization carries a certain humility. It reminds us that our senses evolved to navigate a narrow slice of reality, not to decode the ultimate architecture of existence. The graviton problem is, in part, a collision between the scale of human perception and the scale at which the universe's deepest rules operate. Still, the collision is productive. It drives innovation, not just in technology but in thought. It encourages physicists to borrow ideas from information theory, from condensed matter physics, from computer science. It dissolves the old boundaries between disciplines, forging a more holistic view of nature. In this broader context, the question of whether the universe is hiding the graviton from us may be slightly misplaced. The universe is not hiding anything. It is simply being itself. It is we who are discovering, slowly and sometimes painfully, the limits of the lenses through which we view it. Perhaps the graviton is less a hidden treasure than a signpost. It marks the place where our current understanding ends and something new must begin. Whether that new beginning takes the form of a revolutionary experiment, a radical theory, or a quiet redefinition of what it means to observe, it will owe much to the stubborn mystery of gravity's quantum face. And so the search continues, not because we are certain of success, but because the act of searching expands the territory of the known. In chasing a particle that may never be seen, we uncover new ways of thinking, new questions to ask, and new possibilities to explore. The graviton, elusive as it is, remains one of the most powerful catalysts in the ongoing story of human curiosity. As we stand with one foot in the world of particles and the other in the realm of curved spacetime, it becomes clear that the graviton is not merely a technical problem, but a crossroads. It forces us to choose between extending familiar concepts to their breaking point or inventing entirely new ones. Either path demands a kind of intellectual courage that is rare even in the history of physics. One of the most intriguing developments to arise from this crossroads is the growing suspicion that spacetime itself may be stitched together from quantum correlations. In this view, the smooth geometry we experience is like the surface of a tapestry whose threads are patterns of entanglement. Gravity is then not a force, but a reflection of how densely and in what arrangement those threads are woven. If that is true, then the graviton is not a thread, but a ripple in the weave, a disturbance that has no independent existence apart from the fabric it distorts. You would not expect to find a loose thread in the air. You would only ever see its effect in the pattern of the cloth. This metaphor, though imperfect, captures a shift in emphasis from objects to relationships. The universe may be less like a collection of things and more like a network of influences, a vast web in which every strand is defined by how it connects to others. Gravity, as the universal connector, would then be the most relational phenomenon of all. From this perspective, the graviton's elusiveness is almost inevitable. How do you isolate a relationship? How do you trap a connection? The more you try to cut it out of its context, the more you destroy the very thing you are trying to observe. This line of thought resonates with an unexpected quarter: the study of complex systems. In biology, no single molecule explains the behavior of a cell. In neuroscience, no single neuron explains consciousness. In climate science, no single gust of wind explains a storm. Patterns emerge from interactions, not from isolated parts. Gravity may be another example of this principle, operating at the deepest possible level? If so, then our obsession with the graviton may be a holdover from an earlier era of physics, one that achieved greatness by breaking the world into ever smaller pieces. The next era may achieve greatness by understanding how those pieces conspire to produce something that cannot be reduced further. Yet reductionism has not been wrong. It has simply not been the whole story. The graviton problem may be telling us that the universe is layered, with different kinds of explanation appropriate at different scales. At the level of quarks and electrons, particles reign. At the level of spacetime, relationships may take over. This layered view does not diminish the graviton's importance. On the contrary, it elevates it. The graviton becomes a symbol of the interface between layers, a marker of where our language must change. It is the place where the grammar of physics shifts from nouns to verbs, from things to processes. For those who grew up in an age when every major prediction of physics seemed eventually to be confirmed in a laboratory, this shift can feel disorienting. It challenges the idea that reality is always accessible to us in the same way, that every mystery is simply a matter of building a bigger machine. But perhaps that idea was always a comforting illusion. The universe is vast, and we occupy only a tiny corner of it, equipped with senses tuned to survival rather than to ultimate truth. The fact that we have come as far as we have is astonishing. The fact that we may not be able to go all the way is not a failure, but a reflection of our place within the cosmos. In this light, the graviton is not hiding from us. It is reminding us that knowledge has contours, that every horizon reveals another beyond it. The search for the graviton is less about catching a particle and more about learning how to live with the depth of the universe, a depth that continues to surprise us even after centuries of inquiry. As the narrative unfolds, it becomes impossible to ignore the emotional undertone of the graviton story. There is a quiet tension between the elegance of our theories and the stubbornness of the world. We feel, almost viscerally, that gravity must be quantum because everything else is. And yet, when we try to confirm that intuition, the universe responds with silence. That silence is not empty. It is dense with implications. It tells us that there may be layers of reality that reveal themselves only when we abandon the expectation of direct confrontation. The graviton might be one of those layers, accessible only through the way it shapes the behavior of things we can observe. This realization reframes the role of imagination in science. For much of history, imagination was a tool for generating hypotheses that could then be tested in straightforward ways. Now, imagination may have to carry more weight. It must guide us toward forms of evidence that do not yet fit neatly into our experimental traditions. Consider, for example, the possibility that gravity leaves its quantum fingerprints, not in isolated events, but in statistical textures. The universe may contain patterns of correlation that are inexplicable unless space-time itself is a quantum object. These patterns might be encoded in the distribution of galaxies, in the subtle noise of gravitational wave detectors, or in the behavior of quantum systems subjected to extreme isolation. Such fingerprints would be faint, ambiguous, and open to interpretation. They would demand patience and rigor, but also creativity in deciding what counts as a signal. In this environment, the graviton would be less a target than a lens, a way of interpreting a constellation of clues that point toward a deeper structure. This approach does not satisfy the longing for a moment of discovery that can be dated and celebrated. There may never be a day when a graviton is announced with a photograph and a press conference. Instead, there may be a gradual convergence of ideas, a slow tightening of the conceptual net, until the only remaining explanation is that gravity is quantum. The graviton would then be less a thing we have found than a conclusion we cannot avoid. There is a certain maturity in accepting this possibility. It acknowledges that science is not always about conquering nature, but about listening to it. Sometimes, the universe speaks in a language that does not map neatly onto our instruments, and we must learn to translate rather than insist on hearing it in our own tongue. In the end, the graviton problem is not just about gravity. It is about the evolving relationship between humans and the cosmos. It is about how we adapt when our tools reach their limits, and how our understanding deepens when we allow ourselves to question the frameworks that once served us so well. Whether or not the graviton is ever seen, the universe will continue to curve space-time. Stars will continue to orbit galaxies, and our feet will continue to be pulled toward the Earth. The practical effects of gravity will remain as familiar as ever. What will change is our sense of how those effects arise. Perhaps, many years from now, the graviton will be remembered not as the particle that was never detected, but as the idea that forced us to reimagine the foundations of reality. It may stand as a testament to the fact that the deepest mysteries are not always those we solve, but those that teach us how to think. Looking further ahead, it is natural to wonder how this unresolved mystery will shape the next generation of physicists. The graviton is already a rite of passage in advanced study, a problem that students wrestle with as they learn where the boundaries of current knowledge lie. It is often in grappling with unsolved questions that new ways of thinking are born. In this sense, the graviton may play a role similar to that of the ultraviolet catastrophe at the dawn of the 20th century. That puzzle exposed the inadequacy of classical physics and forced the invention of quantum theory. The graviton problem may be performing the same service today, exposing the inadequacy of our current synthesis and demanding a conceptual leap. That leap may not come from a single insight, but from a slow accumulation of tensions. As experimental techniques in quantum control improve, we may begin to see phenomena that sit awkwardly between quantum mechanics and gravity. Tiny systems behaving in ways that classical gravity cannot fully explain, or perhaps anomalies in gravitational wave data that hint at a granular structure of spacetime. Each anomaly would be small, debatable, easy to dismiss in isolation. Together, they might form a pattern that demands a new story. The graviton would then re-enter the narrative, not as a captured particle, but as a necessary chapter in that story. It would be the name we give to whatever mechanism ultimately reconciles the quantum with the cosmic. There is also the possibility that the graviton will emerge in contexts we have not yet imagined. Historically, many discoveries have come from directions no one anticipated. Radio waves were once a laboratory curiosity. Now they are the backbone of global communication. X-rays were discovered accidentally. Now they peer inside the human body. Perhaps some future technology, developed for entirely different reasons, will stumble upon a signature of quantum gravity and force us to rethink what is observable. Until then, the graviton remains a kind of horizon in the landscape of ideas. Horizons are not walls, they are invitations to travel. They mark the place where familiar landmarks fade and new ones begin to appear. The universe may indeed be hiding the graviton from us, but hiding is not the same as forbidding. It may be that the graviton can be glimpsed only from a different vantage point, one that we have not yet learned to reach. What is certain is that the question will not go away. As long as we care about unifying the forces of nature, as long as we are curious about the origin of spacetime, the graviton will haunt our theories and inspire our experiments. In the quiet moments between breakthroughs, when physicists reflect on the shape of the unknown, the graviton stands as a reminder that the universe is deeper than any framework we impose upon it. It is a symbol of both our ambition and our limitation. A particle that may never be seen yet continues to shape the way we see everything else. As the arc of this inquiry stretches into the future, it becomes clear that the graviton is more than a technical problem waiting for a solution. It is a mirror held up to our methods, reflecting both their power and their fragility. The tools that carried us from the atom to the quark may not carry us from curved spacetime to its quantum roots. This realization does not diminish those tools. It honors them by showing where they reach their natural limits. A microscope can reveal the structure of cells, but not the laws of thermodynamics. A telescope can map galaxies, but not the meaning of time. Every instrument is built for a particular slice of reality, and the graviton may live outside all the slices we currently know how to cut. One can imagine a future in which the graviton is discussed not in terms of detection strategies, but in terms of consistency checks. A viable theory of quantum gravity would need to reproduce every known feature of the universe, from the behavior of black holes to the spectrum of cosmic radiation. If such a theory uniquely requires a graviton-like entity, then that entity would be as real as anything in science, even if no detector ever clicks in response to it. This approach would invert the usual hierarchy. Instead of saying that reality is what our instruments can see, we would say that reality is what our best explanations demand. The graviton would then occupy a place similar to that of the wave function in quantum mechanics. We cannot observe the wave function directly, but we treat it as real because it organizes our understanding of experiments. Of course, this philosophical stance will not satisfy everyone. There will always be those who insist that without direct observation, a concept remains provisional. That tension is healthy. It keeps science grounded and prevents theory from drifting too far into abstraction. But even those who favor hard evidence must concede that the graviton problem has already borne fruit. It has sharpened our understanding of the Planck scale, illuminated the interplay between information and geometry, and highlighted the subtlety of measurement itself. It has enriched physics even in the absence of a final answer. Perhaps the most important lesson is that the universe is not obliged to reveal itself on our terms. It may present us with challenges that require patience measured not in years, but in generations. The graviton could be such a challenge, a long game that outlives its initial seekers. In the meantime, gravity will continue to do its quiet work, bending light, shaping orbits, guiding the evolution of the cosmos. Whether or not we ever isolate its quantum messenger, we will remain immersed in its effects, living inside a structure that is both familiar and profoundly mysterious. The graviton thus becomes a kind of story we tell about the universe, a story about hidden layers and elusive truths. It is a story that reminds us that knowledge is not a destination, but a journey, one that sometimes leads not to answers, but to better questions. At this point in the story, it is worth pausing to notice how far the graviton has already carried us, even without ever showing its face. It has drawn us into reflections on the nature of observation, the structure of space-time, the limits of measurement, and the role of information in the fabric of reality. Few hypothetical particles have ever had such philosophical reach. This reach is not an accident. Gravity is the force that connects everything. It is the only interaction that no particle can escape. That universality is what makes gravity such a compelling candidate for a deeper unification. And it is what makes the graviton so tantalizing. If we could understand gravity at the quantum level, we might finally glimpse the architecture that underlies all physical law. Yet the very universality of gravity is also what makes it slippery. Because everything gravitates, nothing can be perfectly shielded from it. And because nothing can be shielded from it, it becomes impossible to isolate. The graviton is not like a rare species living in a remote habitat. It is everywhere at once, and so it is nowhere in particular. This omnipresence complicates the very notion of background. In most experiments, we can subtract the influence of irrelevant forces, isolating the effect we care about. Gravity refuses to be subtracted. It is the backdrop against which all other effects unfold. Trying to detect the graviton is like trying to hear the sound of silence in a room where silence is the default condition. Still, silence has texture. In a quiet room, the faint hum of air conditioning or the distant rumble of traffic becomes noticeable. In the gravitationally quiet universe, perhaps there is a comparable hum, a barely perceptible irregularity that betrays the quantum nature of space-time. This is why some researchers speculate about fundamental noise in the geometry of the cosmos, a restless graininess that no amount of refinement can smooth away. If such noise exists, it would not announce itself as a discrete particle. It would be more like a persistent whisper, a deviation from perfect smoothness that accumulates over time and distance. Detecting it would require instruments of extraordinary stability and patience, capable of distinguishing true cosmic texture from every conceivable source of interference. And even then, interpretation would be fraught. How would we know that the noise came from gravitons rather than from some other, equally exotic feature of reality? The graviton, as always, would remain just out of reach, its presence inferred rather than observed. Yet perhaps this is enough. Perhaps the graviton does not need to be caught to fulfill its role in physics. Perhaps its true function is to guide us toward a deeper synthesis, to serve as a conceptual bridge rather than an experimental trophy. In that sense, the graviton is already doing its job. It is pushing us to question assumptions we once took for granted, to explore new mathematical landscapes, to invent new experimental philosophies. It is reminding us that the universe is not a static object to be cataloged, but a dynamic process to be understood. The story of the graviton is, at heart, a story about curiosity, about the refusal to accept that there are corners of reality forever closed to inquiry, even when evidence seems to suggest otherwise. It is about the willingness to chase an idea to the edge of possibility and to learn from the chase itself. Whether or not the graviton is ever glimpsed, its pursuit will continue to shape the way we think about gravity, quantum mechanics, and the nature of existence. It will remain a quiet companion in our explorations, a reminder that the deepest truths are often the hardest to hold. As we approach the end of this long arc of reflection, a certain pattern becomes clear. Every time we try to pin gravity down, it dissolves into something more subtle. Every time we sharpen our instruments, the target seems to retreat into the conceptual distance. The graviton has become less a quarry and more a compass, pointing not to a destination but to a direction of travel. That direction leads us toward a physics that is less about objects and more about structure, less about capturing events and more about understanding constraints. In such a physics, the graviton may be replaced by a deeper principle, one that unifies geometry, information, and quantum behavior in a way that makes the old question of detection seem quaint. If that happens, the history books may record that the graviton was never found because it was never quite what we thought it was. It will be remembered as the name we gave to a problem, a placeholder for a truth that could not yet be spoken. But history may also surprise us. It often does. It may be that some future generation, armed with technologies and concepts we cannot yet imagine, will look back at our doubts with gentle amusement. They may find a way to coax a whisper of spacetime into a measurable signal, to turn inference into observation, after all. Until then, we live in a universe whose most intimate workings remain partly hidden. Gravity continues to bind us to the Earth, to the Sun, to the galaxy, while its quantum nature remains an open question. That tension is not a flaw in our understanding, but a testament to its depth. The graviton, elusive and perhaps unknowable, stands as a symbol of that depth. It marks the place where the familiar ends and the profound begins. It invites us to keep asking, to keep imagining, and to accept that some mysteries are not obstacles to be overcome, but companions on the journey of discovery. There is something quietly reassuring in the idea that not every mystery yields on demand. It suggests that the universe is not a puzzle box with a finite number of locks, but a living system whose depths unfold as we grow capable of exploring them. The graviton may be one of those depths, waiting not for better tools, but for a more expansive way of seeing. We began with a simple question: can the particle of gravity ever be detected? Along the way, that question has expanded into a meditation on the nature of space, time, information, and measurement. It has shown us that the hardest problems in physics are rarely confined to one domain. They spill across boundaries, forcing us to reconsider how different pieces of our understanding fit together. In practical terms, gravity will continue to be described by the equations that work so well for planets and stars. Quantum mechanics will continue to govern the microscopic world. For most purposes, this uneasy coexistence is enough. Bridges stand, satellites orbit, computers compute. The graviton does not need to be seen for the world to function, but for those who seek coherence, who want the story of the universe to make sense at every scale, the graviton remains a necessary character. It is the thread that promises to stitch the two halves of modern physics into a single tapestry. Whether that thread is ever grasped directly, or whether it dissolves into the fabric of a deeper theory, remains to be seen. What is certain is that the search has already changed us. It has broadened our imagination, sharpened our skepticism, and deepened our appreciation for the complexity of the cosmos. It has taught us that knowledge is not just a collection of facts, but a process of continual refinement, guided as much by what we cannot do as by what we can. In the end, the universe may indeed be hiding the graviton from us. Or it may simply be revealing that some truths are not meant to be plucked from nature like fruit, but approached asymptotically through ever more subtle forms of understanding. Either way, the graviton remains a beacon at the frontier of thought, a reminder that even in an age of astonishing technological power, the cosmos retains the capacity to surprise, to humble, and to inspire. And so we arrive at the final stretch of this long reflection, not with a solution in hand, but with a richer sense of the terrain we have been crossing. The graviton began as a straightforward idea, a particle to complete the set, a missing tile in the mosaic of forces. It ends as something far more elusive and far more meaningful, a question mark etched into the foundations of reality. The universe may never hand us a graviton in the way it handed us the electron or the photon. There may be no detector that clicks, no graph that spikes, no moment that can be circled in red ink and labeled as the discovery. But that absence need not be interpreted as defeat. It may be the universe's way of telling us that the deepest layers of existence do not always resolve into things we can isolate and name. In the meantime, gravity will continue its quiet, relentless work. It will keep stars burning, galaxies turning, and time flowing at different rates across the cosmos. Every one of those phenomena is a hint a reminder that beneath the smooth surface of experience lies a structure we are only beginning to imagine. Perhaps that is enough. Perhaps the graviton is not hiding from us so much as inviting us to grow into a new kind of understanding, one that values coherence over capture, patterns over particles, and humility over certainty. In that spirit, the search for the graviton is not a chase after an invisible quarry. It is a journey toward a more mature relationship with the universe, a relationship that accepts mystery not as a barrier but as a source of wonder.